welcome again to my Physics Online video lecture series. Today's video, we're going to be continuing our discussion of centripetal motion or circular motion. And in this video, we're going to be looking at going around curves. So imagine that you're driving a car and you come to a curve in the road where it just kind of like turns around, like around a mountain or something like that. And so what we want to look at is sort of two types of curves that you might go around in a car. Specifically, we want to tie this into our previous discussion of centripetal force and kind of ask the question, where does the centripetal force come from for a car going around a curve? Now, as I said at the start, and as the title of this particular video kind of implies, there's sort of two broad types of curves. There's unbanked and there's banked. And in order to understand what's going on, in both cases we need a centripetal force for the car to be able, or the motorcycle or whatever, to be able to go around the curve. So a centripetal force is needed. So you may recall here that the centripetal force Fc must be equal to the mass of the object, the car for example, times the centripetal acceleration, and that the centripetal acceleration is the tangential speed squared divided by the radius, or the angular speed squared times the radius. Okay, it follows that if we were looking at the car moving around the road from above, a curve does something like this, let's say. And so for this part of the road, the car just kind of moving forward at some speed v. But over here, as the car is moving around the curve in the road, this v is changing, and this curve can usually be approximated as a section of a circle whose radius is r. So this gives us the v and the r that we need for this equation right here, the mv squared over r equation. So where do we get that force from? Okay, so essentially we've established either way that this force has to be mv squared over r. Let's say that we have an unbanked curve. So unbanked curve essentially means that the curve is like flat, or the road is really flat, so it just turns around in this plane. Therefore, looked at from the side, if I was to draw a picture of the car, maybe from the top actually, if I draw the picture of the car going around this curve, from the top I can see only one force. This centripetal force must be provided by friction. Okay. From the side, so if I draw the same thing looking at from the side, the car is kind of on what looks like flat ground, and so as it's going around this flat ground, we can figure out different, I guess it's a truck, we can figure out different forces on it. There's a gravity force, mg for gravity, and there's a normal force on each of the tires, but I'm just going to label it from here, F normal. And then the friction force basically points out of the screen at us, force friction. And as you know, that force of friction should be given by, or should be less than, a coefficient of static friction times the normal force. And so that would be coefficient of static friction times m times g. And again, since the ground is flat here, there's a cosine theta, but theta is 0 degrees, and so cosine of theta is just 1. So I'm leaving off the cosine theta term because it's equal to 1 if the curve is unbanked. Now, you may be wondering, why is it that I chose this version right here, the less than μs version, the static friction version. So why static friction and not kinetic friction since the car is moving? And the answer to that is going to be kind of explained in more detail in a future set of these videos when we get into rotational dynamics, when we introduce the idea of rolling without slipping, which is basically how your car's tires more or less interact with the ground. They roll without slipping. Slipping means that you're basically skidding. So if you have skid marks, then your tires were slipping. But usually when you're going around a turn, you're not really skidding. You're just your tires are rolling and you're turning around the turn just like you'd be going straight, not leaving like black marks on the road or skid marks or anything like that. And so when this condition is met, we can say no skidding. When the no skidding condition is met, basically the point of the tire which is in contact with the road has a velocity of 0. V tire equals 0 at point of contact. And that's just how fast is that point of the tire going relative to the road. Now I'm not going to prove why that is in this video. It basically has to do with the rotation of the wheel as your car is moving, and then also the center of mass motion and how those two velocities add together. This is not saying that the wheel itself is not moving. It's not saying that no point on the wheel or car is moving. It's just saying that the one point on the tire that's touching the road happens to have a speed of 0 relative to the road. And if you say, well, the tire doesn't just make contact in one point because, here's my tire and the road actually makes contact with a few points, fine, that's valid. On average, these points have a 0 speed. Some of them have non-zero forward, some of them have non-zero reverse relative to the ground. But on average, it has a speed of 0 relative to the ground. And so on average, what you're using is, again, static friction. So this right here is the form of friction that we need. So going back to our condition that the centripetal force must be the mass of the car times the tangential speed divided by r, we also now have established that the centripetal force must be the force of friction static. And so that must be less than mu static times m times g. And so if you put these together, what you get is that mv squared over r, which is equal to this, must be less than mu static times m times g. And so now divide both sides by m, and what you're left with is v squared over r must be less than mu times g. Or put differently, you need a coefficient of static friction that is greater than v squared over r times g. So that gives you how much static friction you need in order to safely maneuver the car around that turn. You can also rearrange to get, the other possible thing you might want to solve for, or one of the other things, you could solve for a radius, you could solve for a speed. G is kind of set because we're assuming that this is on Earth, but you could rearrange to get that the maximum speed that you're allowed to have going around the curve is equal to the square root of mu, that is the coefficient of static friction, times the radius of curvature for the curve times g. So this gives you your maximum speed that you can go around that curve and stay on that curve with. Any faster and you're going to be slipping out, and if you slip out, then you go to kinetic friction, which means that you actually have even lower friction, so now you slip out even worse. Okay, so that is the unbanked curve. You basically have to use friction to stay on the road. What does the banked curve look like? So the banked curve basically means that your car, as it's going around the road, is actually on a slight incline. So instead of the road being flat like this, the road is inclined like this. We'll call this angle theta. And so this is like the front of your car. Okay. So here's the front of your car, here's the front wheels or whatever, here's your windshield, so on. So you're coming in the direction, V is in the direction of out of the screen, essentially. Here's the headlights. Here's the steering wheel. Here's you at the steering wheel. Anyway, where does the force come from in this particular problem? Well, you can have friction. You can have static friction, and that force actually can be either this way or this way as needed. So this would be my direction of static friction. Presence of this force of friction essentially means that we end up with a range of possible radii that this car can safely navigate the banked curve. Now, if you're wondering, like, where is the circle in this uniform circular motion, essentially this bank is making the car move around a circle whose radius is defined somewhere over here. So essentially, like, your banked curve is kind of curving around like this. And maybe I can get a little picture from a Daytona Speedway or something on here. Alright, so here's one from Daytona Speedway. And if you're looking at it, you can see that the road is kind of like angled at a pretty steep gradient. So this is basically like a banked curve. Okay, it's helping the cars to have some essentially additional force towards the center of the circle that they're trying to make around beyond just friction. So where's this additional force coming from? Well, if I draw the free body diagram for this car, again, I have gravity acting downward, mg, and I now have a new force, the normal force, acting in this direction, F normal. And I can also have some friction force, maybe in this direction or maybe in that direction. We'll say F friction, static. And again, this direction right here, if I draw my dashed line, this is my centripetal direction. So this is to center of circle. And so my centripetal force in this case, Fc, must be some component of this friction force and some component of the normal force. We could maybe call it F in R and F friction static R. And so how much of each of those is there? Well, again, if this right here is angle theta, then R is in this direction, and that makes this angle also theta. Okay, and so essentially the angle theta in this diagram here would be this angle, and ergo this angle right here, theta. Okay, and so this right here is 90 minus theta. So using a little bit of trigonometry, what we come up with is our diagram, and from trigonometry it should be clear that the component of the normal force that is contributing to centripetal force is the sine component. And so we can say something like the normal force times the sine of theta. And then we also have friction, or we stated we had friction present. Remember that friction, if we added it to this diagram, could either be pointing this way up the curve or this way down the curve. So this is friction. This could also be friction. And we'll put a little question mark because we don't know whether it's up or down the curve. but this angle right here is also angle theta. This angle right here is also angle theta, and so that goes with cosine. And so we have the normal force either minus the force of friction, so that would be mu s times normal force, and times the cosine of theta, cos theta, must be less than the centripetal force, and that in turn must be less than the normal force times the sine of theta minus the coefficient of friction times the normal force, which is your friction force, times cosine theta. But this side it's added instead of subtracted. So this kind of like bounds your upper and lower possible values for centripetal force. And as stated with this previous unbanked curve, that kind of bounds your upper and lower values of V max. So remember that this right here is in turn m times v squared over r. And so it follows that you can find a maximum value for your speed given a banked curve and angle and given a coefficient of friction. Essentially, this is stating now that your maximum speed or your minimum speed, there's actually now a minimum speed needed, falls within this range Fn times r over m times sine of theta minus mu times cosine theta must be less than v squared. So we could also just take the square root of all this. So that's less than v is less than square root of r times normal force divided by mass times sine theta plus mu cosine theta. Now this term right here, because we have a subtraction, this term actually could come out to an imaginary value, and if that's the case, then essentially it means that your minimum speed is 0. So if you go 0, then you're not going to fall down the curve. But it could also end up being that there is a sort of like imaginary value. So essentially, bear in mind that imaginary values on this side just means the actual minimum is 0. Okay. What's the simplest case of this thing? So simplifying case says let mu s equals 0, so no friction. So this is your banked curve without friction. If that's the case, then these less than signs kind of disappear, and we just simply get v is equal to the square root of r times the normal force divided by the mass times the sine of theta. Okay? Because these two sides of the less than and the greater than both end up having a 0 for this term, and so they both have the same value, and that means that v must be exactly equal to this value for the car to go around with no friction and stay at the same level. Now there's a further sort of thing to note, which is that this in cosine theta equals w term, this is basically saying that f normal is equal times the cosine of theta is equal to mg. Now that's slightly different than our typical, where we say that the normal force is mg times cosine theta. So notice that the cosine theta is kind of flipped sides. And the reason for that is that we have this centripetal motion going on, and so there's sort of a force needed to kind of keep the car in the same location. Now with that said, in some sense this gets thrown off a little bit if we don't simplify to allowing no friction. Alright. So with this simplifying case, we actually can note that we have n sine theta equals something and we have n cosine theta equals something. And if you divide those two things by each other, sine divided by cosine is tangent. And so tangent of theta is going to be equal to the centripetal force, Fc, divided by the weight, Fg, or whatever you want to call it. And so this is mv squared over r divided by mg. And so you end up with tangent theta is v squared over rg. In a similar way to how we found that mu s was v squared over rg in the unbanked case. So there's a sort of symmetry kind of sort of baked in. That said, this in some sense is still a valid thing to find. It basically means that you're finding the angle theta for which, given the radius of curvature and the speed that your car is going to be moving, you won't need friction. And so now from that you could figure out what's the buffer that friction is going to provide given this size of your curve. So friction means that you're going to be allowed to go a little faster or a little slower than the speed that we've found here. So the speed we found here basically is v without friction, or v squared without friction, is the square root of g times r times tangent theta, or in other words, tangent theta is v squared over rg. And as I said, there is a sort of symmetry here, because recall that if you were to ask, if I have a car or something, if I put a block on a ramp and I slowly raise the angle until the block starts to move, at what angle does that occur? The answer is the tangent of that angle should equal the coefficient of static friction. And here we have a sort of parallel to that, because the tangent of theta, v squared over rg, looks suspiciously like mu s is v squared over rg. When we say this has to be greater than, you could say it's like greater than or equal to. Alright, so that's kind of it. Now what happens if we include friction? Well, in some sense what you can do is go through and find this speed without the friction present, and then ask, supposing that I have a coefficient of friction of whatever, 0.05 or 0.1 or 0.2 or whatever. Supposing that I have that coefficient of friction, what values of speed can I safely handle this curve at above and below this value that we found here? So this video has gone again a little over, because I had two kind of topics into one, which is one topic being curves and the two topics being what if they're banked and what if they're not banked. So there is a bit in this video. I hope that the extra time is worth it for you. I hope that you learned something from it. I hope that you found something interesting in it. And either way, thanks for watching.